Today, we begin one of the most fundamental concepts in mobile robotics, localization. Before a robot can plan a path, avoid obstacles, or make intelligent decisions, it must first understand its own position in space. Think about humans walking in a new city. If we don't know where we are, even a map becomes useless. Similarly, for a robot, navigation without localization is meaningless. In robotics, localization refers to estimating the robot's pose, which includes both its position in two dimensions and its orientation. Orientation is extremely important because the same position with a different heading leads to completely different motion outcomes. Localization acts as the foundation layer for higher level tasks like mapping, path planning, and autonomous exploration. Without it, the control system might function correctly. Motors may run properly, but the robot may still fail in reaching the desired location. So essentially, localization answers a very simple but powerful question. Where am I right now? Everything else in mobile robotics builds upon this answer. Now we'll see what is odometry. Odometry is essential internal position estimation based on wheel movement. When wheels rotate, encoders measure the angular displacement, and using robot kinematics, we calculate how much the robot has moved. This is called dead reckoning. Why dead reckoning? Because the robot does not use any external reference. It simply trusts its previous position and calculates the next one based on motion commands. It is computationally simple and does not require heavy processing. That is why odometry is widely used in indoor robots, warehouse automation system, and educational platforms. However, odometry has an important limitation. It assumes perfect motion execution. In real environments, that assumption rarely holds true. Even small imperfections in movement begin to accumulate. So, odometry gives us continuous estimate, but we must question how long we trust it. In this slide, there are two equations that is given. For a differential drive robot, delta S and delta theta is given. In this equation, R represents the wheel radius, L distance between the wheels, delta phi R and delta phi L are the wheel rotations. Odometry is simple, inexpensive, and widely used. In this slide, we observe the kinematic model of a differential drive robot. A differential drive robot has two independently driven wheels. By varying the velocity of each wheel, the robot can move forward, rotate, or follow curved trajectories. If both wheels move at the same speed, the robot moves straight. If one wheel moves faster than the other, it follows a circular arc. If wheels rotate in opposite direction, the robot rotates about its center. The mathematical relationship between wheel velocities and robot motion is derived from rigid body kinematics. The pose update equations depend on wheel radius, wheelbase distance, and encoder measurements. This model works perfectly in theory, but remember, the equations assume exact parameters and perfect rolling motion without slip. Even a tiny deviation in wheel diameter or encoder reading introduces a mismatch between the theoretical motion and actual motion. This is where real-world robotics becomes challenging. Now we come to the critical limitation, that is the error accumulation in the case of odometry. Odometry errors do not appear suddenly. They grow gradually. Every time the robot updates its position, a small error is introduced. That error becomes the starting point for the next update. So errors accumulate over time. This leads to something called post drift. The robot believes it as at one location, but physically it may be somewhere else. Imagine long distance navigation inside a warehouse. After several meters of movement, the deviation may become significant enough to cause navigation failure. The most dangerous part is orientation error. A small angular deviation early in the motion can result in large positional deviation later. This is because heading error changes the direction of motion continuously. So even if linear displacement is accurate, a small rotational inaccuracy can cause exponential growth in positional error. That is why long-term reliance on odometry alone is risky. Odometry errors are generally categorized into two types: systematic and non-systematic. Systematic errors arise from mechanical imperfections. For example, if one wheel is slightly larger than the other, even if commanded equally, the robot will curve slightly. Similarly, incorrect wheelbase measurements affects turning radius. These errors are consistent and predictable. Because they are repeatable, we can reduce them through calibration procedures. Non-systematic errors, on the other hand, are unpredictable. Wheels slip on smooth surfaces, uneven terrain, sudden obstacles. These introduce randomness. These errors are difficult to model mathematically because they depend on environmental interaction. In real-world robotics, non-systematic errors are more problematic because they cannot be easily corrected through calibration. So in practice, both mechanical precision and environmental conditions influence localization performance. Now we move from deterministic thinking to probabilistic thinking. Instead of assuming exact position, modern robotics treats localization as a probability distribution. First, the robot predicts its next position using the odometry. This step is called motion update. But instead of saying I'm exactly here, the robot says I'm probably somewhere in this region. Then comes observation update. Sensors such as LiDAR, camera, or IMU provide environmental feedback. The predicted pose is compared with sensor measurements and map data. This matching process determines how well the prediction aligns with reality. Finally, the estimate is corrected using sensor feedback. This reduces uncertainty. This predict, compare, correct cycle continues continuously. This probabilistic framework allows robots to operate in uncertain environments more robustly than pure deterministic models. This slide conceptually illustrates how error grows over time. Initially, position estimation may be very close to actual position, but as time progresses, uncertainty spreads. Think of it like drawing a circle repeatedly with slight hand movement error. The deviation increases gradually. In robotics, this uncertainty can be mathematically represented using covariance matrices. The longer the robot moves without correction, the larger the uncertainty region becomes. So the question becomes, how frequently should we correct? Frequent corrections reduce uncertainty but increase computational load. This trade-off between accuracy and computational cost is central for localization system design. Now we'll see an example of a odometry drift. Consider the simple example commanding the robot to move in a square path. Theoretically, after completing four 90-degree turns, it should turn to the starting position. But in practice, it rarely does. Small rotational errors during each turn accumulate. Even a 1-degree error per turn results in 4-degree final misalignment. Over longer distances, this becomes significant. These examples clearly demonstrate that orientation error has multiplicative impact on position accuracy. So drift is not just a theoretical concept, it is observable in simple experiments. This is why external corrections mechanisms are essential. Why mathematical? Now we'll see the mathematical insight into error growth. If the heading error is delta theta, and the position error after traveling distance d, the position error that is happening will be d into the heading error. Thus, larger distance amplifies smaller angular errors. Rotational errors are more dangerous than translational errors. Why odometry alone is not enough? Odometry is simple, cost-effective, and suitable for short durations. However, it cannot self-correct. It has no awareness of ground truth. In slippery environments or dynamic surfaces, wheel-based estimation become unreliable. For long-duration missions such as autonomous explorations or warehouse logistics, relying solely on odometry is insufficient. Therefore, modern robotics relies on sensor fusion, comparing multiple sensors to compensate for weakness of each. Odometry provides short-term smooth estimation. External sensors provide long-term correction. This complementary approach improves robustness. Now we'll see the solutions to the odometry error. To overcome drift, multiple sensors are integrated. IMU sensors provides orientation stability. LiDAR provides distance measurement to surroundings. Cameras enable visual odometry. GPS help in outdoor environments. Advanced estimation techniques like extended Kalman filter and particle filter mathematically combine predictions and observations. SLAM goes one step further. It builds a map while localizing simultaneously. These techniques do not eliminate uncertainty but manage it intelligently. The key idea is redundancy. Never trust a single sensor completely. By combining information sources, robots achieve higher reliability. Let us summarize. Odometry is a subset of localization. It's a method of estimating motion using internal sensors. Localization is broader. It includes prediction correction and uncertainty modeling. Odometry is fast and simple but suffers from drift. Localization frameworks incorporate sensor fusion to reduce error. In robotics, accurate localization determines the success of navigation. Without localization, autonomy is impossible. As we move forward in this course, we will explore advanced probabilistic techniques and SLAM algorithms that enable robots to operate in complex real-world environments.